Okay, so just to recap while we're recording, I'll make y'all's final exam review this weekend. I'll post it into Canvas. We'll probably start working on that maybe next a week from this Wednesday. Give y'all maybe Thursday and Friday or Wednesday, Thursday, Friday to go over it in class. We'll test on what did I say, Monday the 13th, right? Yeah, and that'll be Form B. And then on Tuesday the 14th, we'll go over it. And then on the 15th, that's when finals start. Okay, and then you'll have a holiday story with more details to come that I'll assign tomorrow. And that'll be due on Friday the 10th. Okay, and then we'll share some of those stories anonymously on that what it would be Wednesday and Thursday before we get out. Okay, so warm up here. This is f of x is 3 minus 2 times 4 to the x. Evaluate and simplify f of negative 0.5 without a calculator. I said without a calculator because this is the type of question you might see then on that final exam, review, and on your third test, because it'll all be without a calculator. You'll have answer choices, of course. And I don't know if I mentioned, but the computer program only does 4 answer choices, A, B, C, and D. So first of all, what type of function is this? Is this a polynomial function? Polynomial function? No. It's exponential. Why? How about that? Why is it exponential? It's to the power of x, right? The variable's in the exponent, and the base is what? It is greater than 1, but it's also a number, right? That's important. Remember, if the base is also a variable, that's the Aleph function. It's not exponential. So you have a numeric base, and then you have a variable exponent. That's the hallmark sign of an exponential function. Now, we're just trying to evaluate it. So all we have to do is plug and chug. And remember, it's about communicating or indicating our method. So we're going to write f of negative 0.5. And when I'm evaluating, instead of working straight down, I like to work left to right just once, okay? And then we work straight down on that side. So that's 3 minus 2 times 4 to the negative 0.5 power, okay? So that's just plugging in for x. Now I'm going to work straight down and simplify. Where do we go from there? Oh, what's that? Turn the 4 into a 1/2?
Yeah, since the power to a 0.5 turns it into a half.
Yeah, okay. Let's talk about that. First of all, can I multiply those two together and call that 8? No, because the bases aren't the same, all right? But what I can do is, as Brady said, I can rewrite negative 0.5 as negative 1/2. Okay, that's kind of how we've been working with things in a non-calculator situation. Your calculator doesn't care if you typed it in as a decimal or as a fraction. Now, to get rid of both the negative exponent and the fractional exponent at the same time, we can rewrite that as what? The negative takes it to the bottom, yes? And then the 1/2 puts it under a radical. So that's going to be 1 over the square root of 4. Very well, yeah, the square root of 4 is 2. Yeah. So again, that's important. That's kind of working with the skills that we had earlier in the year. That's 1 over 4 to the 1/2, which is 1 over the square root of 4. But you should be able to go straight from here to here. Okay. And now we can simplify that. That gives us something to evaluate. The square root of 4 is 2, so we're left with 1/2. And now we multiply 2 times a half is 1. We get 3 minus 2, 3 minus 2. And 3 minus 2 is 1, right? No.
1/2 times 2 will equal 1.
Very good, very good. You don't want to stumble at the end. Careless mistakes. 2 times a half is 1, and 3 minus 1 is 2. But 1 would make a good answer choice as well, right? On the test? Yeah. Careless mistakes typically happen at the end when people, oh, someone's charging.
Yeah.
That's yours. And then you got mine. You just did a swap, Rooney. Oh, no, that one was vacant. Right. Yeah. Okay. Yeah. Because I know who has that. All right. So again, the answer would be 2. Again, notice the notation here. You know, you start on the left-hand side with the plug-in equals, and then you work straight down. You don't have to keep writing f of negative 0.5 unless you absolutely want to. Okay. All right, everyone sufficiently warm? A little warmer today than it was yesterday. Both outside and inside, right? Okay. So yesterday we learned kind of what exponential growth functions, how the bases relate to each other, how exponential decay functions, how the bases relate to each other. And then we quickly talked about how the growth and decay functions are related to each other when the bases are reciprocal. So let's just quickly review that. We said that for exponential growth, when the base is greater than 1, the bigger the base, the steeper the graph, right? And then it's the opposite. The opposite is true for decay. The smaller the base, the steeper the graph. And it's because, you can quickly tell, it's because the 10 and the 1/10 base and the 5 and the 1/5 and the 3 and the 1/3 and the 2 and the 1/2, those pairs of graphs are reflections of each other across the y-axis, right? So if 10 to the x is the steepest, you know, exponential growth, and when you reflect that across the y-axis to get 1/10 to the x, that's going to be the steepest decay. And 1/10 then is going to be smaller than 1/5, 1/3, 1/2. Okay. So remember, steep is a it's a scalar quantity. It doesn't have a sign. It could be steep in any direction. So when I say steep, I mean that it goes to infinity faster on one side and it goes to 0 faster on the other. Okay. So we could say this, we proved it down here, but let's go ahead and state this in general. Okay. B to the x, y equals b to the x, and y equals 1 over b to the x are going to be reflections of each other across the y-axis. What's another name for the y-axis? What's the equation for the y-axis? X equals 0. Yeah, same thing. Okay. And we proved that algebraically. I think we verified it actually for the 5 and the 1/5. But that's kind of how the growth and decay are related to each other. Now we did meet another base yesterday, and I think y'all had seen E before yesterday, but we talked about E the number, right? Not E the letter. And we said E is the natural base. It's named after Leonhard Euler, the Swiss mathematician, who is the most single productive mathematician of all time. He's written he made more individual breakthroughs mathematically than anyone else before or since on his own. And believe it or not, he lost sight in one of his eyes. I forget which eye it was, late in life. And he is actually more productive after he lost the sight in one eye than he was before he lost sight in one eye.
That means he got less, that means he got distracted less.
Have you heard that before?
No, I'm just thinking that because 50% less eyes mean 50% less focus.
Well, my gosh, I was going to tell a funny joke and a quote by Leonhard Euler. When they asked Leonhard Euler how that was possible, he said, and I quote Leonhard Euler, well, it was because I was less distracted. Oh my gosh, Brady has the same sense of humor as Swiss mathematician Leonhard Euler. How about that? How about that? And that's anticipating a punchline right there. Yeah. No, I mean, it's humorous, but yeah, he was less distracted. So, okay, so let's go ahead and meet our parent function e to the x. I think we've seen him before, but just for the record, here he is. After today, you're 100% accountable for knowing what he looks like and the properties of the graph of e to the x. Okay, if I can draw a snap straight, there we go. Vertical, horizontal, and we can actually lower the x-axis a little bit, something like that. Okay, so remember E is approximately 2.7. That would be good enough for you. 718 is typically what we talk about. It's an irrational number, which means it can't be expressed as a ratio of two integers, but it's also called a transcendental irrational number. Okay, so what does the transcendental part mean? It just means that it's not going to be like a solution to an algebraic equation, like the square root of 2, the square root of 5, square root of 3. All of those are also irrational numbers, but those are algebraic irrational numbers. Numbers like e, pi, phi, the golden ratio, those are all transcendental. Okay, but because it's greater than 1, it's going to be growth. So let's go ahead and get the common characteristics that we know we're going to have. I'll use orange here. So we know that we're going to have a horizontal asymptote on the x-axis, and we know we're going to pass through the point 0, 1. And now because it's growth, all you got to do is draw it coming from here, passing through there, and then it gets very, very, it grows very, very fast, very rapidly. So if I didn't give you the equation of that, that could just be any random exponential growth function, right? We don't really need to label anything other than that. It's only important when we have more than one of them graphed on the same coordinate grid to show the relative steepness, okay? So this would be then our parent function f of x equals e to the x. All right, let's talk about a few characteristics then. What would be the domain of this function? All real numbers. That's right. All real numbers. Or if you want to get infinity involved, Brady, what would it be? Leonard? Euler, Mr. Euler, what would it be in terms of infinity? You said infinity, but you mean what in interval notation? There you go. There you go. Right. Right. I'm calling you Leonard now. Or Lenny. How about that? Now that's going to be true for all exponentials. Okay. Every single exponential function of the form y equals a times b to the x is going to have a domain of all real numbers. What's the range of this function?
Well, it's obviously greater than 0.
Obviously, right? Obviously, even with one eye. Yeah, so let's see, we can write it like this. It's the set of all y such that y is strictly greater than 0. Or if we're going to write it in interval notation. Oh, by the way, remember in interval notation, it's not required. Contextually, we know those are x values, but if we put x epsilon, it kind of helps. Same thing here. If we put y epsilon, we know it's going to be from 0 to infinity, and 0 would get the parentheses instead of the bracket. Okay, intercepts. Let's talk about the y-intercept. Of course, that's going to be the point 0, 1. And x-intercepts. What are the x-intercepts of this graph? Does it have any? No. Yeah, none, right? We'll just say none. All right, symmetry. Remember, when we talk about symmetry, we kind of went over this very, very quickly. We're talking about one of two things. We're talking about either y-axis symmetry, which is the folding symmetry on the y-axis, or rotational symmetry, which is putting your finger down at the origin and spinning it 180 degrees. Does this one have either one of those? No, it doesn't. So we'll say none. Remember, if it does have y-axis symmetry, we call it an even function. If it had rotational symmetry, we call it an odd function. So no symmetry. Intervals of increasing or decreasing. Well, this function is what? Increasing or decreasing over its entire domain? Increasing. So here's the word that we can say. We can say that it is monotonic. Monotonic, or the other term we can say is strictly increasing. Monotonic means what? Mono, of course, we know means one, right? Like mono Sarahs. Every year they can have no more than one Sarah on the team. Monotonic means one tone, doing one thing and one thing only. Luckily, I don't speak monotonically, right? That would be boring. Like if you've ever seen Ferris Bueller. Anyone seen that great movie? Ferris Bueller's Day Off? Yeah. Ben Stein, the teacher. Bueller. He teaches very monotonically, very boring. Strictly is the same thing, one thing and one thing only. So that just means one thing and one thing only. It's going uphill anywhere and everywhere, okay, from left to right. And then the end behaviors. Let's go ahead and write those out. How do we show the analysis for the end behaviors? as x, yeah, of f of x. You could say the of part first, of f of x as x goes to negative infinity. And then the limit as x goes to positive infinity of f of x. Yeah. So what's the left end behavior? 0. And then the right end behavior is infinity, right? Or DNE. So again, I mentioned yesterday that that's one of the most kind of remarkable features of any exponential function, whether it's growth or decay. It's the fact that their end behaviors are dramatically different. Okay, dramatically different. Is there anything else about this function that's worth saying? It's orange, right? Well, mine is orange. Is y'all's orange? Probably don't want to say that then. E to the x is always orange, right? No, that's not good. Oh yeah, yeah. We can actually state that. Perfect. Let's come over here and say that f has an HA at y equals 0. Very good. And again, we know that the graph is only affected by that on the left end. There's one other feature I want to talk about. One-to-oneness. Have y'all heard of that? One-to-one. F is a one-to-one. You can write it either one of these two ways. Function. 1:1 means 1-to-1. It's like it's a proportion, a ratio, or you can write it out with hyphens. A one-to-one function is a function, of course, but the one-to-oneness is kind of exactly what it sounds like. For every Mickey Mouse, there's only one Minnie Mouse, right? And for every Minnie Mouse, there's only what? One Mickey Mouse. They are a faithfully monogamous couple, right? They're one-to-one. They're a one-to-one couple. Okay. Now, to be a function, we know that what? Every x can have no more than one y value, right? But can you have multiple y values, or can you have the same y value coming from different multiple x values? Yes, right? Like just like x squared. Y value of 25 can come from x equals -5 or x equals +5. So to be a function, the x values have to be faithfully monogamous to the y values. But the y values can see other x values on the side, right? Yeah. So that's not one-to-one, right? Now you can assign gender roles to those if you want. I don't know. But to be a one-to-one function, for every x, there can be no more than one y. And for every y, there can be no more than one x. Okay. So to be a function, it has to pass the vertical line test. To be a one-to-one function, it has to pass the vertical line test and the what? Horizontal line test. Yeah. Does our parabola x squared pass the horizontal line test? No, our graph of x squared. Does the graph of x squared pass a horizontal line test? No, okay, because we have one y value coming from two different x values. So it's still a function, right? The x values are faithful, but the y value is not, okay? So to be a one-to-one function, it has to pass both the vertical and the horizontal line test. So let's go ahead and state that. It must pass both the vertical and horizontal line test. Now, those types of functions that are one-to-one, we call them invertible. You don't have to write that down. But an invertible function is nice because it has an inverse function that is also a function. So if you're into like coding messages, a one-to-one function would be a good function to use because there's only one way to code the message, and there's also only one way to uncode it. What's the decode? There you go. There's only one way to decode it. You wouldn't want to code a message and have the person on the other end have like two or more different ways to decode it, because then the message is lost. So one-to-one functions are good in that respect. They have an inverse that's also a function. Okay, so it's also one-to-one. Okay. Can anyone think of any other characteristic about functions in general that we've talked about at any time in our math careers that's worth mentioning here? Any other features or characteristics or traits? No vertical asymptote. Yeah, there's no discontinuities. Let's go ahead and say that. We could say then that F is continuous. Good. We've talked about continuity quite a bit this year, right? F is continuous for all real numbers. That's very, very important. From left to right, there are no vertical asymptotes. There are no holes. There are no jumps. None of that good stuff. Good. So yeah, there was still something else to discuss. Anything else? Can anyone think of anything? Does it have any local extrema, local max or local mins? A local min? Well, local max and local mins, those are going to be like hills or valleys, like vertices, right? So this one has no local. I'm going to put slash relative because those two words are interchangeable. And I'm going to say max or mins. Max or mins combined is called extrema. In other words, it has no vertical turning points. It has no vertical turning points. It doesn't do vertical about faces. No vertices. Anything else? That's kind of a lot of information, right? Yeah, I think that's pretty exhaustive. So now that we've seen e to the x, and we know it's like 2.7, we know all of these traits, characteristics about this graph, we should be able to then generate relatives of this graph without a calculator, namely transformations. Yay, right. So let's go ahead and look at example 6 then. We want to sketch the graph of 3 minus e to the x minus 1. And once we sketch it, then we can talk about some of the characteristics, all right? So anytime you're sketching a function without a calculator, step 1 is to identify the parent function. What's the parent function here? Is it x squared? I'm just guessing. No. It's e to the what? It's e to the x. Yeah, e to the x. So whether it's off to the side or in your head, you get this idea, you get this vision, right, of your parent function e to the x. Okay, that's your parent function. We'll go ahead and write that in here. Parent function. Actually, I'm feeling a little bit brave today. I'm going to go ahead and say that that's the mother function. Yeah, same thing, right? Mother function. It just sounds naughty, right? Mother function. The next step, once you identify the parent or the mother function, or the daddy function, you can call it too, is to put it into standard transformation form. So let me go ahead and review what standard transformation form is. We're going to have standard transformation form. And we've already seen this year, but here it is. It's going to be y equals a times f of b times x minus c close plus d, right? And we know that there's two dynamics that are at play here. The inside part are the b and the c. Those affect the graph horizontally, stretch or compress versus shift. And then the outside a and d affect the graph vertically. They affect the y values. So that's the first dynamic. The other dynamic is whether it's multiplied, a and b are the multipliers, which are your dilations, stretches and compressions, or reflections. And then you got your shifts, which are your adders and subtractors, C and D. Those are just translations, okay? We put them all together and we can figure out what A, B, and C and D are going to do to any starting graph. So is F now in standard transformation form? Not quite, right? There's one last thing we have to do. And what is it? The 3 in the front should go where? At the back, right? So that's negative e to the x minus 1 and then plus 3. Now, if you want to add parentheses to help yourself see layers, perfectly acceptable. X minus 1 is the inside part. So what does it mean to be inside an x squared function? It means to be in parentheses before you square it. What does it mean to be inside a square root function? Well, it means to be under the radical. What does it mean to be inside an exponential function? It means to be in the exponent. That's where the x is. So what would our a value be? The benefit of doing it this way is, remember, we can just do it in alphabetical order from left to right, which takes care of your dear Aunt Sally rules, multiplication before addition, subtraction. What's your a value? -1. So what does that do to this parent function over here? Let's label it, okay? This right here is an x-axis reflection. So we'll just say x-axis reflection. And that's going to be the same for any function, all right? The easy way to think about it is one of two ways. You know, your old standby function that you can compare it is x squared, which opens up, and negative x squared, which opens down. But the other way to think about it is it's in front of the entire function. The entire function are your y values. So now you have the opposite y value. So just like put your fingers at like 5 and -5, and now take the opposite of them. 5 becomes -5, -5 becomes +5. Those are trading places like this, right, across the x-axis. So it's an x-axis reflection. All right, so you can come over here to your little sketch, and you could start like just showing what it's going to look like. So now it's going to look like this, right? You want to do this as a sequence of transformation. So it's going to open down. And that's it. That takes care of the A's and B's. The A's and B's are always going to affect the shape and the orientation of your graph. We should probably write that. A and B affect the shape and the orientation. Okay. And by that, I mean whether it opens up or down. Okay. Once you know what A and B do to the graph, then it's just a matter of picking it up and moving it somewhere. Left, right, up, down, left, right, up, down. You no longer change the shape or orientation. All right, so what does the -1 do when it's inside? Right 1. It's, remember, if it's inside, it's opposite of what it appears. So it's right 1, and then the +3, which is outside on the ground floor, is up 3. Good. So your C and D affect not the shape and orientation, they only affect the location. They're just going to move it someplace new. All right. So if you think about it, you can come over here, and it's nice with notability. You can just kind of lasso your graph and just imagine moving that orange graph right 1 unit. Did you see when I moved it right 1? Watch this. There it is. I'm going to move it right 1 unit. It doesn't really affect it that much, right? Okay. I moved it right 1. Nice. But if I move it up 3, ooh, that's going to be significant. Yes? Okay. Because when I move it vertically, that's going to change the location of what distinguishing characteristic? The horizontal asymptote, which always is at 0. So if you move everything up 3, where does the horizontal asymptote now go? Up to 3 as well. Yeah. So you're always going to have, in this case, you're always going to have, for an exponential function, you're going to have a horizontal asymptote at y equals d every time. And then depending if you're reflecting it across the x-axis or not, your graph may live above it or below it. All right. So let's go ahead and sketch our final graph. We want to be able to sketch a really nice version of the final graph. Okay, now notice the last thing that we did by transformations was to move it up 3, which changed the horizontal asymptote. But the first thing we do when we graph it is to sketch the horizontal asymptote. It's the last thing that we do, but it's the first thing that we do. Last thing that we do, but it's the first thing that we do. Because remember, asymptotes are like gravity. They affect the graph. So What I'm going to do is say 1, 2, 3. There's 3. And I'm just going to come in here and draw that horizontal line. Now, remember the shift to the right didn't really affect it much, okay? But I do know that the orientation and shape is this. I know it's decreasing below the horizontal asymptote, yeah? Decreasing below the horizontal asymptote. Well, here's the deal. I could just draw something like this randomly. But if I move it right, look what happens. Look at my y-intercept. Right now it's at 2. If I started drawing it over here, I have a y-intercept that's negative. If I move it to the right, I have a y-intercept that's 0. If I move it to the right, I have a positive y-intercept. So because of the horizontal shift, I could end up with a y-intercept that's either negative, 0, or positive. Is there any freaking way to tell without a calculator if my y-intercept is negative, 0, or positive? Because I do want you to be at least that accurate. Yes. How? F of 0. Very good. So for exponential functions, because their domain is all real numbers, you're always going to want to find the new y-intercept. You don't have to track the old y-intercept that was at 0, 1. I don't expect you to follow where that point goes, okay? But I do want you to find the new y-intercept instead. You need to know where the new vertical horizontal asymptote is, and you need to know whether it's increasing or decreasing above or below. But don't worry about following the old y-intercept. So here we go. When I plug it in, I am going to write f of 0. I can plug it either into the standard transformation version, or I can plug it into the original version, right? They are equivalent. Now, the standard transformation form is useful for sketching, but it's not always the most useful for evaluating. So I tend to just plug it back into the original. Would you be okay with that? Okay, oops. So I'm going to do that. Here we go. It's going to be 3 minus e to the 0 minus 1 is negative 1. Now, much like the warm-up, I think I can keep going here, right? This is going to be 3 minus 1 over e. And now I'm like, crap. I don't know what 1 over e is. Does anyone here know what 1 divided by 2.718 is? No, I don't either. But remember, all we're trying to do here is figure out if the y-intercept is negative, 0, or positive. Can I determine that without a calculator? Yeah. What do I know about 1 over e? Is it bigger than 1, or bigger than 0, or less than 0? Bigger than 1, less than 1. It's bigger than 0. 1 over e is bigger than 0, but it's less than 1, right? Less than 1. That's important. So if you have 3 and you take away something that's smaller than 1, is it going to be positive still or negative?
Negative.
It's going to be positive. Euler, you just lost it, right? So in other words, this is like 3 minus a smidgen, right? That's a good word. 3 minus a smidgen is going to be greater than 0. That's all you need to write. In fact, you don't even need to write 3 minus a smidgen. Here's all you have to do. If you know 1 over e is less than 1, 3 minus something that's less than 1 is still greater than 0. That inequality right there speaks volumes, because look what you just told me. You just told me f of 0 is greater than 0. Now, I don't know exactly what it is, but I do know it's like 2 point something. So now when I'm drawing my final graph, I think I'm going to draw it crossing. I'm not going to even care if you have it crossing kind of in the right scale. Usually I don't even put tick marks. I just put 1 dot right up there at 3. I am going to check to see if you have it crossing in the correct location, whether it's positive, negative, or 0. Now be careful. I've seen some of y'all drawing the graph over here on the left-hand side, and I've seen it like mine. See right here on the very end, mine is curving back down. Yeah, I would probably forgive what I drew here because it's going to the horizontal asymptote. But remember that this function does not curve back down there. So depending on how quickly you draw it, if you draw it doing this, and then you do that, you think I'm going to count that, right? No, that's totally curving away. So Just be careful. That's why we draw the asymptote first. Draw it going towards the asymptote. And you always want to draw the asymptote, okay? Always. If you don't draw the asymptote, you're not going to get credit. All right. It's a guideline. Literally, it's a guideline. And then we do want to go ahead and put arrows on the end. Why? Yeah, it's continuous and the domain is all real numbers. That shows that it goes on forever and ever and ever and ever. Okay, now that we have this, we can answer questions like, what's the domain of this function? All real numbers. You can do that with your eyes closed, but what's the range? Less than 3, right? So negative infinity up to 3 with the what? Parenthesis or bracket? Parenthesis, right? Or you could say it's the set of all y such that y is strictly less than 3. Okay. This function is monotonically what? F is monotonic. Good. Monotonic decreasing or strictly decreasing. You say one or the other over its entire domain. Okay. So there you go. That's all we got today. I think that's good enough. Memorize your parent function. Might we have a quiz tomorrow over a real quick sketch like this? Maybe. Your worksheet is out there. It's awaiting you. So make sure you're practicing a little bit every day so that you're reinforcing the skills and concepts and ideas that we talked about in class. So anyway, enjoy the rest of your Moose Day. Moose. And happy birthday, Pink Floyd. No, Winston Churchill. The Wall. Yeah. Thriller also came out on this day in '82. So happy birthday, Michael Jackson, or something like that. All right.